Welcome to Math 2318. This is section 2.9. In this section, we're looking at two slightly different topics. One is we're given a basis for a particular space, and we're looking to see how we would represent a vector relative to that basis. We're also going to look at the rank of a matrix, the rank or dimension of the column space of a matrix, and the dimension of the null space of A. So, here in question 1, we are given two vectors. These vectors form a basis. And relative to that basis, vector x is representable as 3, 2. So what does that mean? So here's V1, here's V2. When I say that x relative to basis B is 3, 2, that means that x is 3 times the first basis vector plus 2 times the second basis vector. And so if you grind that out, that's just 3 times 1, 1, plus 2 times 2 minus 1. And you get 7, 1. So vector x is 7, 1 in the E1, E2 basis. But relative to this basis is representable as 3, 2. So they want us to show this in terms of a picture. All right, so looking at this picture, we know that B1, so here in picture B, B1 points to 1, 1. And vector basis B2 was 2 minus 1. So you see down here along the bottom, you've got B1 and B2. If you remember, relative to our normal bases, so if I represented our normal bases, so here's I, which is E1, and here's J, which is E2. So normally our basis vectors are relative to the basis, which is along the two axes. Here we have B1 is here, here's B2. So our vector x, which is 7, 1, so here's x in red, 7, 1 is there. And that's 7, 1 again relative to E1, E2. But relative to the new basis, how do I do that? Well, here's 3B1, here's 2B2, and the sum of those two, using the parallelogram rule for adding vectors, looks like our vector x. All right, so let's take a look here in question 2. We have two basis vectors, B1, B2. Vector x is 4 minus 2. So the question is this: how do we represent this vector x in terms of the new bases? So that means I'm looking for two numbers, C1 and C2, where when I form the linear combination, I get x. So our goal is to put B1, B2 in, put in x, row reduce this, and see what would the numbers be. Alright, so I couldn't get a 1 easily, so I'm just going to use the 4 itself and get rid of the minus 9. So I multiplied top row by 9. I multiplied the bottom row by 4, added them up. At this point, I've got a 7 and a 28. I can get a 1, so divide through by 7. And so now use this 1 to make a 0 above it. Just simply add them up. And now to finish it off, I can divide through by 4, giving me that my constants are 2 and 4. So relative to that basis, x in its coordinates is 2, 4. All right, in question 3, we are given two basis vectors, and they're going to ask us to represent x, y, and z relative to that. All right, so let's take a look. So first off, where are these? So let's see. B2 points this way. Here's B1. All right, so x is normally here going -2, -1. So how do I get to that point using B1 and B2? Well, let's see, I'm already pointing down, so that's the same as B1, which is 1. I need to reverse the direction of B2. All right, so I need to reverse it around and then go 1, 2. So that's why it's a -2. What about y? Where's y? Y is pointing here. All right, so let's see. Here's y at 1, -2. All right, well, B1 just needs to go farther, and that's why that's a 2 in terms of B1. Now B2, let's see, already goes 1, so 2, 1. All right, what about here in this one? In this one, let's see, z is pointing at -3/4 and a +2 up. Yeah, +2 up. And so how do I get there relative to B1? Well, I need to turn B1 around and go up 2 of them. All right, so -2 B1. B2 needs to turn around as well. And when it turns around, all right, that's going to make it negative, and I need to go a -3/4. All right. Now in this question, we're looking at the column space and the null space of matrix A. So matrix A, what's the size of it? Well, it's got 4 rows, 5 columns. And they've row reduced it for us as well. So let's see, A is 4 by 5, and so if it's going to work on an object through multiplication, its size must be 5 by 1. And so if I take a 4 by 5, multiply it by a 5 by 1, its image is going to be 4 by 1. All right, so that means that A, its domain is something in R5, and its image is something in R4. So now I look at the echelon form, and I look for how many pivot columns. There's 3 pivot columns. So that says that the rank of the matrix A is 3, which is the dimension of the column space. So again, the dimension of the column space is the same as the rank of matrix A, which is 3, which came from the number of pivot columns in the echelon form. Pivot columns were in column 1, 2, and 4. And so if you take columns 1, 2, and 4, you get a basis for the column space of A. All right. We have that the rank of the matrix plus the dimension of the null space has to be the number of columns of A, which is 5 because we're going from R5 to R4. All right, so that was our basis for the column space. How do I get my basis for my null space? All right, well, I need to solve the problem AX equals 0. So I'm using the reduced, the echelon form. Here's the 0 on the last column. And now I completely reduce this. So let's see. I'm going to need to take this 1 and make a 0. Alright, so by doing that, I make a 0 above it. So this 1, make a 0. Alright, so that's cleared out. Now I'm going to take this 1. I see some zeros there already. Alright, and so by doing that, I see, first off, the last row. So x5 is free. x4, which is here, is minus 3x5. x3 is free. x2 is in terms of x3 and x5. And tracing out the first row, I get the relationship for x1. Alright, so x1 looks like the following. Here's x2. x3 and x5 were free, and x4 was minus 3x5. And so now if I split this in terms of x3 and x5, I get my basis for my null space, which, remember, the dimension of the null space is 2, so my basis has 2 vectors. They are from R5 because there are 5 components. Alright, a few extra things also in the chapter. So if A is n by n, we're going from Rn into Rn. If the rank is n, that means the dimension of the column space is also n, which means that this mapping is onto, and so the columns span all of Rn. So again, this notion about the linear mapping is onto. If all of this is true, that A has full rank, A is invertible, and the dimension of the null space is 0 because it only has the 0 vector in it. All right, in question 5, what do we have? We have A is 6 by 9. So A is going from R9 to R6. So here's my dimension of 9. We know that the rank of A plus the dimension of the null space, that sum must be 9. They tell us that the subspace where we have all the solutions where it's 0, which is the null space, is 7. And so that says that the rank of A must be equal to 2, which is the dimension of the column space of A. All right. So that means that over here in its image, it's going to span a set which is in R2, a subspace of R6. All right, proceeding in the same way. A is 7 by 9, so We are having a mapping going from R9 to R7. Again, the rank of A plus the dimension of the null space is 9. They're telling us that the rank of A is 4. So 4 plus 5 is 9. So the dimension of the null space is 5. All right. And so that concludes section 2.9.